Hello everyone, I'm Mrunmayi Mungekar from UCLA, and today I'm going to present my PhD work on directed shape morphing of soft Kirigami deployables. So, as the name suggests, this work has given me the opportunity to create these wondrous robotic structures, which are created from a planar fabrication process by a self-directed morphing process using the Japanese art of cutting paper or kirigami. So, to set the foundation for this whole thing, let's look at the robotic structures that we could possibly create. So, structures which are actuators or mechanical traps are very complex in form. However, as engineers, we are always on the lookout of more novel methods to make this process cost effective, intuitive, and of course, a potential ease of scalability is always looked out for. So, in my PhD tenure, I looked at the marvelous feats of designs that all many times go unnoticed around us. For example, in nature, we see a small embryo developing into a fully formed baby, or plants and leaves which wrinkle and grow into these beautiful patterns. None of these organisms actually require any design intervention to do so. They have everything that is required embedded into their initial form, and when the time is right, they simply move from one form to another. Can we use this technique in creating such robotic structures in engineering? So to do so, I created this planar composite in which one sheet of material is stretched and another unstretched sheet is connected on top of this. However, this unstretched sheet is not connected as is. It is cut into a particular pattern using the art of kirigami, such that I can actually control what the final shape is going to be. And as per our intuition, as we leave the constraint on this substrate, the whole composite pops out of plane, giving us a 3D shape, which in this case has been determined by our kirigami design. Of course, we can go one step further, and if these sheets of materials are flexible, we can actually add another sheet of kirigami, and we can make these structures bistable, setting a platform for creating more dynamic robotic structures. However, we are not completely there when it comes to no intervention design morphing. So, what we did is we included shrinking sheets into these structures. So, shrinking sheets are these pieces of thermoplastics, which are basically children's toys, in which a sheet simply contracts on heating. So, we use this shrinking sheet and we add a kirigami layer to it. Now, you can actually forget about this composite as long as it's not required. And when it's required, you simply take it out, you heat it, and you see it grow and morph into a 3D shape. There is no design intervention in this whole thing. Everything required has been already embedded into the planar form. So, you see, what I achieved through this PhD thesis was create these fully formed 3D shapes from planar precursors without any design intervention and a completely self-directed morphing process. So this gives us majorly four things: no design intervention, self-directed morphing, a complete planar fabrication process, and of course, with advancements in additive manufacturing that could create more complex electronic embedded robotic structures. Three, equipment frugal manufacturing, considering the easily available materials used or equipments that might be required for the whole process. And because of all of this, a potential ease of scalability of these structures. So, well, as robotic engineers, what else do we want? So, I hope you had as much fun with these structures as I had with them through my PhD tenure. Thank you very much.